Alright, so today I'm going to be explaining this important paper with the title Improved Techniques for Training Score-Based Generative Models. This NeurIPS paper in 2020, again by Stefano Ehrman. Score-based generative models can produce high-quality image samples comparable to GANs without requiring adversarial optimization. However, existing training procedures they are limited to images of low resolution and can be unstable under some settings. We provide a new theoretical analysis of learning and sampling from score-based models in high-dimensional spaces, explaining existing failure modes and motivating new solutions that generalize across datasets. To enhance stability, we also propose to maintain an exponential moving average of model weights. So you're familiar with this Langevin dynamics. For example, we have a total number of t iterations, and starting from initial condition, we can get different samples. And this z, as I said, is just a normal distribution with mean 0 and variance I. So suppose we have a neural network that we have a S theta. For example, we have learned some score network. And of course, this is an approximation of a score. We can approximately generate samples using Langevin dynamics if we replace it by this learned score function. So you know these backgrounds. Another background is score-based generative models. Suppose we have an underlying data distribution and consider a sequence of noise scales that sigma 1 is greater, so gradually we are decreasing the noise. And there are different noise scales. For example, L different noise scales. If we order them, for example, sigma 1 is greater than sigma 2, then reference 1 proposes to estimate the score function for each p by just training with this loss. So we have expectation of this norm, L2 norm squared, and all expectation can be efficiently estimated using empirical averages, as every student in machine learning knows. So when trained to the optimum, the noise conditional score network almost everywhere, assuming enough data and satisfies this if we have enough data and model capacity. So after training, it generates samples if you use this Langevin dynamics here. We provide a pseudocode in algorithm 1, and the approach amounts to sampling from p sigma 1, p sigma 2, and so on. And those alpha I are here. So we want to choose these noise scales. When the range of pixel values is between 0 and 1, the original work recommends choosing the noise level as geometric sequence. It is reasonable that the smallest noise scale is very, very smaller than 1, because we sample from perturbed distributions with descending noise scales, and we want to add low noise at the end. However, some important questions remain unanswered, which turn out to be critical to the success of NCSNs on high-resolution images. So what is these questions? The author says that is sigma 1 equal to 1 appropriate? If not, how should we adjust it for different datasets? The second question the author asks is geometric progression a good choice? And the third question the author asks, Professor Ehrman, is L equal to 10 good across different data sets? If not, how many noise scales are ideal? So we provide answers to the above questions. So initial noise scale. The algorithm of annealed Langevin, which is a kind of Langevin dynamics, is an iterative refining procedure that starts from generating coarse samples with rich variation under large noise. Before, I think this is part 4. Part 4 of this current playlist for denoising score matching. I don't know why I think I've explained it before, but maybe I've explained it before. But let's carry on. So the initial noise scale sigma 1 largely controls the diversity of the final samples. In order to promote sample diversity, we might want to choose sigma 1 to be as large as possible. However, an excessively large sigma 1 will require more noise scales and make annealed Langevin dynamics more expensive. So we present analysis to guide the choice of sigma 1. So the performance, when perturbed with this normal distribution, the empirical distribution becomes this. For generating diverse samples regardless of initialization, we naturally expect Langevin dynamics can explore any component when initialized from any other component. So this is the performance, all the performance of Langevin dynamics is just governed by this score function. So technique 1, choose that sigma 1, that scale, to be as large as the maximum Euclidean distance between all pairs of training data points. For example, in this proposition, they defined R, which we want to find the upper bound of the expectation of that, to be this normalized PI. So we have an upper bound for that. And this upper bound is the distances between individual points in the data sets. These are the data points in our training set. And taking CFR10, for example, the median pairwise distance between all training images is around 18. So sigma 1 equal to 1 implies that if you look at the proposition, you substitute it, it becomes this, and is unlikely to produce diverse samples. There are other noise scales that, however, an extensive grid search on these noise scales can be very expensive. To give some theoretical guidance on finding good noise scales, we consider a simple case where the data set contains only one data point. And so this figure is training loss curves of two noise conditioning methods. Because for high resolution images, we need large sigma 1 and a huge number of noise scale. And so in order to sample from NCSN with annealed Langevin, we need to specify the number of sampling steps per noise scale, T, and step size epsilon. So the authors in reference 1 recommend this choice for epsilon and this choice for T. We revisit this section 3.2 that I explained, where the dataset has one point. Annealed Langevin dynamics connect to adjacent noise scales by initializing Langevin dynamics with samples obtained from PX. For better mixing of Langevin dynamics, we hope that this approaches one across all noise scales. So technique 4 is choose T as large as allowed by computing budget and then select an epsilon that makes this equation 4 maximally close to 1. So there are good guidance in this paper. And what is the conclusion? They say our techniques significantly improve the training and sampling processes, lead to better sample quality, and enable high fidelity image generation at high resolution. Although our techniques work well without manual tuning, we believe that the performance can be improved even more by fine-tuning various hyperparameters. Future directions include theoretical understandings on sample quality of score-based generative models. So it's interesting. As well as alternative noise distributions to Gaussian perturbations. Yes, everyone uses Gaussian perturbations, so that could be another research direction.